this is working. Yeah. So, I don't know if you have noticed, but last year we were scaling Ethereum. And we have achieved quite a lot. And now we have scaled Ethereum, so now we can change to agentic AI, right? Not really. Scaling is not working like that. So we are scaling, and scaling continues. And large part of the scaling is scaling actually the networking stack behind Ethereum. So I will be speaking about this. I'm not going into too much technical detail. It will be a little bit technical. I hope you like that. So I have a slide about the Ethereum networking stack in a nutshell. What you should know is that there is the execution layer, the execution layer clients. They form the peer-to-peer network, and that is the consensus layer clients, and they form the network. Each one have their own peer-to-peer functions: discovery, managing peers, syncing the network, syncing the chain, syncing the state, syncing the blocks. Mempool on the EL side, getting the transactions, and then on the consensus side, discovery, peer management, syncing, diffusing blocks, doing attestations, doing the blob dispersal, and then sampling these blobs now. This is part of the scaling already. Each one of these uses different protocols. I mean, not each, but we have a bunch of protocols. And I won't be going into the details of these protocols. Just notice that there are many of them. We have discovery protocols, V4, V5. We have that P2P in the execution layer side. We have P2P on the consensus layer side. And there's also connection between the two clients running on the same node. This is the engine API. And then all this is running in an environment, right? So we have minimum nodes requirements. Nodes are different. We have a bunch of nodes, 10,000 nodes. And they are geographically dispersed. There are nodes in Africa, there are nodes in Australia, and in many other places. And then this is the system that we want to scale. And, well, the problem with scaling is that when you are scaling, any of these can become a bottleneck. So it's not like, yeah, we scaled one part and now we are done. But because then another thing pops up as a bottleneck, and then you have to think about that. So there are lots of things that we have to think about. There's this menu of things that we have to scale. And, well, I will be speaking about these. So let's start with three of them: discovery, peer management, and syncing the network. Discovery. So discovery, you see discovery when you are starting a node. It has to attach to the network. And the problem with discovery is that discovery is slow in the current implementation. At least this is what I heard. So we have solutions to make it faster. First of all, we have a new protocol. I mean, it's not new. It's all new. There was V4, there's V5, and V5 is much better than this extent. But not the CR clients were not all on V5. Now we are moving them to V5. Then V5 has a feature which is called topic search, which is very useful in some cases. For example, when you are running a node on mainnet, that's fine, you are finding peers. When you are running a devnet or a testnet or a small network with the Ethereum as a technology but not Ethereum mainnet, then you have a problem. You cannot find nodes easily. Topic search is helping in that. And then there is a third thing that actually this is not slow. So I had this post about showing that you can actually discover the whole network of 10,000 nodes in 50 seconds. Like you get to almost 10,000 in 20 seconds. So discovery is fast, and discovery you need it when you start, but discovery also gives robustness to the network. So whenever there is need for a change, you need that to change the network. Next one is peer management. We are in a peer-to-peer network. The CR nodes has peers, the EL nodes has peers. And in EL, we had this problem. There's the same problem also in the CL. That it was hard to find peers who were saying, yeah, come and let's talk to each other, because everyone was full. And we have a few solutions here, and we are implementing them one by one. So inbound, outbound, peer-to-peer separation, that was already there. And then we are adding new ones. What you see there on the curves is how we are speeding up this process in last year, actually. So it took, this is not in seconds, this is more in, I mean, it's the time scale is not 20 seconds here, but here we are in minutes. And you see to ramp up a node, it took 30 minutes before, and now it's basically in 5 minutes, it's ramping up to full capacity. And then there is sync. So to sync, the thing to know about sync is that you're starting your node and you have to sync it. And if that's so, then you cannot start a node, basically. And that's not good for the network, because then they start to die out, and then they would die out. So you have to have a sync which is fast enough. As we are scaling, sync also has to be faster. So we have to work on sync. And there are two use cases here. One is when you are just starting up a new node, and then everyone is helping you start up. And that's the easy case. And then there is the hard case, when there is some problem in the network, and then everyone has to sync, or let's say not everyone, but there are a few nodes, and then 9,000 nodes hanging on them and saying, help me, help me. This is where we need help, and this is where we have to change, and this is where the solution is doing BitTorrent, so syncing similar to BitTorrent, doing things like small syncing. So we have already parts of this in the stack. We have some signals there. It's not yet implemented. Okay. So after we looked at these three things, let's look at the main part, which is the mempool. So the mempool. Scaling the mempool. So we already scaled a lot Ethereum, you see it. And we want to scale things like blobs per slot, and we want to scale also execution. We want to scale the gas per second. Unfortunately, if we want to have more blobs per slot, we need to send them to the mempool, send these blob transactions to the mempool, and we have to send more. If we double the capacity, then we have to send twice as much. And the same happens with gas per sec. So when we are scaling execution, it's nice that we are now at 60, but it also means we need more transactions. These transactions have to arrive to the mempool, then have to be distributed, and then have to be put into blocks. So everything has to scale. The two figures that you see is kind of what's happening in the mempool, like the proportions. On the right side, the red is the blobs, because there I'm showing it as weighted by size. And on the left side, the big one is not the blobs, because there I'm showing it in the numbers. But we are scaling both numbers and the numbers of blobs. So while the proportions might remain, the circles will be bigger. So I will be speaking a little bit about what's happening in the mempool, and then about the kind of proposals on the table to scale it this year. So what's happening in the mempool? Mempool is getting the transactions and then distributing it between all the nodes, ideally. The question is it distributing a transaction to all the nodes? And the answer is yes. So if I today look at the mempool and take a given transaction, then basically everyone has it. This graph is showing down on the x-axis, how many nodes have a given transaction. And basically what you see that everything is on the right side. For every transaction that I'm looking at, everyone has it, basically. And that's cool. That means that the mempool is basically fully synchronized. So whoever is building a block, they have the same picture they can build. The problem is that this is not sustainable. So when we are scaling, there are more transactions, and then everyone would have to have more and more and more. At one point, we cannot sustain that. Another interesting thing to look at, how the mempool works, is how much time transactions spend in the mempool. So you create a transaction, you submit it into mempool, then it's living in a mempool for some time, then it's getting into a block. Then it will get finalized, and kind of this is the time between when you submitted, generated a transaction, and when it's finalized. So this is the first part of the journey. And what you see is that first part of the journey is actually quite fast. So what you see here is kind of individual transactions, and a curve is how they were getting diffused in the mempool. So from 0 nodes to 10,000 nodes, basically. So when you see it shoot up, it means that in 0 point something seconds, you sent it into one node, and then like 90% of the nodes had it. And then it has this curve saying, yeah, and then the rest is getting it slower. This is a different view of the same thing. So it's the same curves. I've just pushed them to the left side. So this is how fast the transactions are getting spread if you put the starting point to the same. So when to when you have submitted the transaction. So why this was, if I was able to go back, was I? Yeah. Here the 0 point was when the transaction was getting into the block. So the guy most to the left was submitted 17 seconds before, and it was an unlucky one who needed 17 seconds to get into a block. Here you see the unlucky guy was submitted and then going there. Anyway, the message is like diffusion is fast in the mempool. The mempool is working. And again, you can look at it this way. And here you see now not individual transactions, because there are many of those, but the statistics. So here what you see, different types of transactions. And the important part is including blobs, which are huge, are being diffused in the mempool very fast. Blobs are a bit slower than the other ones, but still crazy fast. I mean, compared to the slot time, which is 12 seconds. So if you send it, by the time there will be someone building, it's being diffused. And that's good. That's what we want. Except that we want to scale. So we want to push more blobs. We want to have smaller slot times, and so on and so forth. And then these curves will be much worse. So we need to do stuff. So what can we do? So as I said, today, the mempool is working very nicely. We have this fully synchronized mempool among the nodes, at least if your time granularity that you are looking at it is the slot granularity, and that's what we do actually. Every slot, someone is looking at the mempool and saying, hey, I can build stuff. And this is true for both for the normal transactions and for blobs. Tomorrow, this cannot be true. Tomorrow, we cannot keep this notion of fully synchronized mempool simply because we want to scale the transaction amount. It's more traffic for every node, and nodes will not like it. We want to keep the nodes requirements stable. So by definition, nodes should have a partial view of the mempool. And this is first something we need to solve for blobs, because blobs are big. And then when these agents start to send our little transactions, we will have to solve it for the transactions as well, because there will be many of them. OK, so when you want to scale the mempool, there are two main issues. We typically think of the first one, which is we need to reduce the bandwidth. So we need to send the same amount of traffic, but we should somehow use less bandwidth than what we send. And we solved it in the consensus layer. We solved it with Peerdas. So Peerdas was reducing its only sampling. It's doing a probabilistic sampling for the blobs. And it's reducing the bandwidth requirements approximately to 1/8 of the actual data amounts that we are sending. And then there is another technique, which is called GetBlobs. GetBlobs means since the EL already distributed these blobs, the CL is not even distributing it. It's just looking at the EL execution layer client sitting next to it and saying, do you have it? Yeah, I already have it. And then it gives it to him. So the CL is not even dealing about this with the distribution. And with this, the CL bandwidth consumption is even lower because the job is done by the execution layer. But the mempool, the execution layer, instead have all the blobs. And it actually has the blobs which make it to the chain, and it also has the blobs which doesn't make it to the chain. Let's not forget that in the mempool, you have more traffic, because some transactions are not making it to the chain, right? And you also have to handle those. So the mempool is kind of disadvantaged. So we have to solve that lower part. We reduced it in the CL. Here we have to reduce the traffic in the execution layer in the mempool. And then the second problem, which is less known, is that, don't look too much at the figure. That's kind of an old networking telecommunication technology figure. But the thing is, there is something which is which you can call the congestion collapse. So you put more and more demand, more and more traffic into network, and at one point it cannot handle it and it collapses. Until you're not scaling, you don't have this issue, right? Because you set your performance point to a point where you are safe. When you're scaling, you're continuously trying to hit that boundary, and the problem is, if your system is not the right one, then when you are hitting the boundary, you have this catastrophic collapse. You can have this at the system level. The system doesn't function anymore, but you can also have it at the node level. Your node cannot keep up. Maybe it's at the defined boundaries of hardware requirements, but maybe you are running something else on it, or maybe it's overheating a little bit, or whatever, and your node is getting this collapse behavior. So, well, we have proposals to solve both of these. For reducing the bandwidth, we have the Sparse block pool proposal, which is already in an EIP, which is reducing the overall bandwidth in the Mempool. So it's kind of a combination of two techniques. It's one of them is probabilistically fetching only some of them. So only part of the network, 1/6 of the network, will have the full blobs. And then you have also the other kind of technique, which is it's using only, it's taking only, the other nodes are taking only part of the blobs. So only the cells that they need. Actually, only the cells that the consensus layer client will ask them later on, because that's why they need it. This is an EIP. Let's see how that evolves. Then there are other proposals here. So one is different proposals on sharded blob pool. You can do sharding in different ways. So we are speaking of blobs, horizontal meaning the blob direction. You can do horizontal sharding in different ways. You have to decide basically based on what you decide which shard the blob belongs to. You can do it based on the source address of the sender. You can do it based on the hash of the transaction, or you can come up with other things. These are being debated. Vertical sharding, which is kind of cutting the blob in pieces and shards by the cell index. And then this is still blobs, and then you can do sharded mempool. So once you realize that you have to also scale the mempool, you have to shard the mempool as well. It's not something we have an EIP yet, but that's something we have to think about. And then there is the other problem, the congestion collapse. So again, there are some ideas here, EIP 8077, which is basically saying when I'm announcing a transaction, and for this you have to know how it's working in the mempool. In the mempool, I'm just announcing I have this and this and this and hash. And then you as a node, you are seeing he has those hashes, he has those hashes, he has those hashes. And then you have to decide what you pull, but you only see hash. So what you do? And the problem is when there is congestion, you just see more and more hashes popping up, and you don't know what to do. You can just fetch randomly, basically. So this is adding more metadata so that you can intelligently fetch, which has the advantage of you will not have nonce gaps, so transactions which are behind gaps which cannot be included. And you can also filter by address. So you can do things like I'm only focusing on part of the address space, I'm instancing this address, etc. Then there's the second one, which is specific kind of congestion collapse. We have this mechanism which is called replace by fee. So you send, and this is specific for blobs, you send a blob transaction, and then you have to replace it. You have to substitute it, and it's typically because you have to give different fee caps. Why you have to do that? Because the market fee is not what you were thinking it will be. So you have to replace it. And when you have to do it in the current system, you have to resend the whole blob transaction. And then it's getting redistributed again. And that's very wasteful. So this EIP is solving this problem. It's saying when you are changing all the fees, let's redistribute only the new fees and not the whole blob content to the nodes. And then there is a third proposal, which is called blob pool tickets, which is, well, you require tickets to submit blob transactions. I'm not going into detail of that. That's being actively worked on. Okay, yeah, so this is how we scale DL. And then I have two little slides for you on scaling other things. So, well, was not CL related. One is what I would call the low-latency peer-to-peer toolbox. So I was putting this together last year. It's not that I invented any of these. These are techniques known in peer-to-peer research for some time. The good thing is we are starting to apply them and kind of make them fit the system that we have. So there are a bunch of techniques, segmentation, scheduling and prioritization, using QUIC, better transport than TCP, doing encoding, read Solomon fountain codes, network coding even, or optimizing the overlay, which means currently you can easily send messages back and forth over the ocean. That just feels like a waste. But optimizing that is actually very difficult because if you optimize it too much, then you have these clusters of networks. So anyway, there are techniques on that, and we can start applying all these one by one. Some of them we started. Segmentation is already done partly with the cells and cell-level messages. Encoding, we use this from encoding. Quick transport is being introduced in all the CL clients. So yeah, all these are being done. And last, we have Peerdas, which is doing its columns of, and it gives us this 8 times gain in the distribution of Blob content. We have research on other techniques. I was doing this Peerdas version 2, which is kind of a combination of a bunch of techniques targeting a bunch of blobs. 256 blobs, so it has block level encoding. It's kind of making it such that when finally we decided that this will be the content, blob content of a block, then the system is helping that happen, and it has many low latency techniques. Yeah, that's it. Plus many other things that others are working on. So the networking part is about to improve, and I hope we can provide more scaling to Ethereum also this year. Thank you.